The first ionization energy is the minimum energy required to remove 1 mole of electrons from 1 mole of gaseous atoms in their ground state. The electrons are removed from neutral atoms, producing gaseous ions with a charge of 1 plus. In equation form, X in the gaseous state forms X plus in the gaseous state and 1 electron. Energy must be supplied to overcome the attraction between the negatively charged electron and the positively charged nucleus. Ionization energy is therefore always positive and is measured in kilojoules per mole. The strength of this attraction depends mainly on nuclear charge, atomic radius, electron shielding, and the energy of the electron being removed. A greater nuclear charge usually increases ionization energy because a nucleus with more protons attracts electrons more strongly. Distance also matters. An electron farther from the nucleus experiences a weaker electrostatic attraction, so it requires less energy to remove. Inner shell electrons shield an outer electron from the full nuclear charge. Greater shielding therefore makes the outer electron easier to remove. Across a period, the first ionization energy generally increases. The number of protons increases while the added electrons enter the same main energy level. Shielding changes only slightly, so the increasing nuclear charge attracts the electrons more strongly. The atomic radius also decreases, bringing the outer electron closer to the nucleus. This makes the electron more difficult to remove. The increase across a period is not perfectly regular. The subshell and orbital containing the electron can also affect the ionization energy. In period 3, the first important exception occurs between magnesium and aluminium. Magnesium has an electron configuration ending in 3s2, so its first electron is removed from the 3s subshell. Aluminium ends in 3s2, 3p1, so its first electron is removed from the 3p subshell. A 3p electron has more energy and is slightly more shielded than a 3s electron. It is therefore easier to remove. This is why aluminium has a lower first ionization energy than magnesium, despite having a greater nuclear charge. Another exception occurs between phosphorus and sulfur. Phosphorus has 3 electrons in the 3p subshell. According to Hund's rule, they occupy 3 separate p orbitals. Sulfur has 4 electrons in the 3p subshell, so 2 electrons must share the same orbital. These paired electrons repel each other, making one of them easier to remove. Sulfur therefore has a slightly lower first ionization energy than phosphorus. Down a group, the first ionization energy generally decreases. Each element has an additional occupied electron shell. The outer electron is farther from the nucleus and it experiences more shielding from inner shell electrons. The nuclear charge also increases, but the effects of greater distance and greater shielding are more significant. The outer electron is held less strongly, so it requires less energy to remove. This trend helps explain the reactivity of group 1 metals. Group 1 metals react by losing their single valence electron. Down the group, this electron becomes easier to remove, so the metals generally become more reactive. An atom can lose more than 1 electron. The energies required to remove these electrons are called successive ionization energies. The first ionization energy removes an electron from a neutral atom. The second removes an electron from an ion with a charge of 1 plus. The third removes an electron from an ion with a charge of 2 plus. Successive ionization energies always increase. After each electron is removed, the ion becomes more positive. The remaining electrons experience a stronger attraction to the same nucleus, so more energy is needed to remove the next electron. A particularly large increase occurs when all the valence electrons have been removed. The next electron must then come from an inner shell. This electron is closer to the nucleus, experiences less shielding, and is much more strongly attracted to the nucleus. The position of this large jump tells us how many valence electrons the atom has. Suppose the first 3 ionization energies are approximately 738, 1451, and 7733 kilojoules per mole. The largest increase is between the second and third values. This means that 2 electrons are removed before an inner shell electron must be removed. The atom therefore has 2 valence electrons and is most likely a group 2 element. A large jump after the first ionization energy suggests 1 valence electron. A large jump after the second suggests 2, and a large jump after the third suggests 3. Look for the largest proportional increase between consecutive values. Do not simply select the largest number in the data. In an exam explanation, identify the electron being removed and compare its attraction to the nucleus. State whether nuclear charge, distance, shielding, subshell energy, or electron pairing changes. Then explain how that change affects the energy required to remove the electron.